Welcome back! Up to this point in our C programming journey, we've covered the mechanics of moving data around. We've built for loops, processed user inputs, constructed custom functions, and manipulated memory addresses using pointers. But if you are coming from Python, Java, or C++, you are about to hit a major architectural wall. Look at these isolated data types floating in memory. In modern languages, you would organize them using an object-oriented class. However, in C, classes do not exist. This presents an immediate problem. Operating systems, network stacks, and game engines are built in C. How do these massive systems manage complex, multivariable entities, like an employee with an ID, a name, and a salary, or a physics object with velocity and mass, without the organizational framework of a class? The answer is the structure, or struct. A struct is a custom data type that allows you to manually group heterogeneous variables into a single cohesive unit of memory. Today, we are going to build that architecture from the ground up. We will construct basic structs, nest them into hierarchies, optimize them using structure pointers, control how the CPU pads their memory layout, and explore alternatives like unions and enums. Mastering structs requires a shift in mindset. You have to stop relying on the compiler to organize your data automatically and start designing your memory layouts like a bare metal systems engineer. The core mechanical capability of a struct is unification. Unlike an array, which forces every item to be the exact same type, a struct lets you bundle integers, floats, characters, and arrays under a single unified name. Let's see how we define a struct blueprint. On the left, we type the struct keyword, followed by the name employee. Inside the curly braces, we declare our members: an integer for ID, a character array for name, an integer for age, and a float for salary. On the right, the compiler recognizes this blueprint and prepares a digital container with 4 distinct memory slots sized for these data types. Defining the struct doesn't allocate memory, it just creates the blueprint. To actually use it, we instantiate a structure variable by typing struct employee m1. Now our memory container is active and waiting for data. To target a specific member inside this container, we use the dot operator. By typing m1.id equals 101, we reach directly into the struct and assign the value to that specific integer slot. But assigning a string to the name member exposes a classic C trap. If you try to write m1.name equals Mark, the compiler will throw an error. In C, a string is a character array, and you cannot directly assign a new array to an existing one using an equal sign. To bypass this, we have to copy the characters into the array directly. We include the string header file at the top of our script and use the strcpy function to manually move our string into emp1.name. C gives you direct, unfiltered access to memory. That means the language won't hold your hand when packing complex data like strings into storage arrays. You are explicitly responsible for how every byte is placed. Once you have data safely inside a struct, managing it becomes highly efficient. If you want to duplicate an employee's data, you don't copy each variable individually. You simply assign one struct variable to another, like emp2 equals emp1, and C duplicates the entire enclosed memory block at once. Real-world data is rarely flat. An employee doesn't just have a name and an ID, they belong to a department, which has its own ID and name. To model this, C allows you to place one structure completely inside another, a concept called nested structures. There is a strict compiler rule here. The internal structure must be declared before the parent structure can use it. In this memory container, we define the department struct first. Only then can we embed it as a subbox inside the larger employee architecture. To access data buried inside that internal box, we chain the dot operators together. We write emp1.department.departmentName to navigate down through the nested memory levels, one step at a time. Nested structs perfectly map complex logical relationships into code. But every time you nest a struct, you add its byte count to the parent object. As these objects grow heavier, moving them around your program increases the total memory load. Look at what happens to performance when we pass a massive nested structure into a function. By default, C passes data by value. The system is forced to duplicate that entire massive memory block just to hand it to the function, creating unnecessary overhead. The bare metal solution to this bottleneck is the structure pointer. Instead of copying the actual data, we declare a pointer variable with an asterisk. We pass a single, lightweight memory address that simply points the function back to the original structure. But introducing a pointer changes the rules of syntax. You can no longer use the standard dot operator to access the struct's internal data. When accessing a struct member through a pointer, the dot is strictly replaced by the arrow operator, a dash followed by a greater than sign. If we write a function to update an employee's department year, we pass the pointer in, and inside the function, we write ptr arrow model year equals year. We reach through the memory address and update the value at its source. Using structure pointers ensures that as your data models grow more complex, your execution speed remains consistent, avoiding the overhead of massive memory copies. Let's zoom in on the CPU. If you build a structure containing a 1-byte character and a 4-byte integer, you might expect it to consume exactly 5 bytes. Yet if you check the memory footprint, it often consumes 8. This chart shows exactly why that happens. CPUs process data in fixed-size chunks. To ensure your struct aligns with how the processor reads memory, the compiler injects empty, wasted bytes into the gaps. This process is called structure padding. While padding speeds up processing, it wastes RAM. Developers can manually minimize this waste by declaring their struct members in descending order of size. By grouping the largest data types at the top and the smallest at the bottom, we pack the memory grid efficiently and reduce the required padding. If you need extreme memory conservation, perhaps you are programming a microcontroller with severe RAM limits, C offers an alternative to the struct called a union. This comparative matrix illustrates the fundamental difference. In a struct, on the left, every member gets its own separate physical space. The total size is the sum of all members. In a union, on the right, all members share the exact same physical memory location. The total size of the union is simply the size of its largest single member. The operational constraint of a union is absolute. Because the space is shared, you can only use one member at a time. If you assign a value to an integer member and then assign a character to a different member, the integer is instantly overwritten. Structs are designed for complete organizational mapping, where you need all variables active at once. Unions are used for mutually exclusive scenarios, like an API response that will return either a success payload or an error code, but never both simultaneously. Writing struct employee every single time you want to declare a variable creates friction for developers. We can clean up this code using the Typedef keyword. Typedef creates a clean, single-word alias for an existing data type. Instead of explicitly calling out the struct keyword, you can assign it an alias, streamlining instantiation down to a single word. We can apply a similar layer of polish to constant values using enums. An enum is a method for grouping predefined constant options, like coffee cup sizes, states in a state machine, or days of the week. In this code snippet, we define an enum for cup size. Instead of checking if a variable equals 1 or 2, you check if it equals regular or large, making conditional logic much more readable. Tools like Typedef and Enums do not change how the CPU manages memory. What they do is make the strict architecture of systems code maintainable for human engineering teams. We started with isolated, chaotic variables and grouped them into cohesive structures. We nested those structures to reflect reality, optimized their travel using pointers and the arrow operator, manually compressed their padded memory layouts, and polished the syntax for readability. Every struct definition and arrow operator brings you closer to controlling the physical layout of your data. Next, we will take the final step into manual resource control, dynamic memory management, using malloc and calloc alongside proper error handling. You now have the foundational tools for building complex data structures in C. Thanks for watching, and I'll see you in the next one.